Hello, and welcome to your second math review lecture on probability theory and graph theory. We're just going to do kind of a basic foundation here today in this video, and then of course we'll do some examples together in class as well as continue the rest of the lecture together. By the way, I won't mention this in most videos, but if you want the slides to follow along, you can always find them on our course GitHub. I upload the HTML there, but you can also find them if you go to our course GitHub and look under lecture slides. So let's talk a little bit about probability. And to do that, we're really going to go back to the foundational basics of what probability is and how it works. And these tools are what allow us to do all of the really complicated things that we do in statistics and data science. These are sort of the Lego bricks that brick by brick allow us to build something huge and actually useful that we might use every day in data science. So in order to talk about probability, we first need to talk about probability spaces. Probability spaces have three really important components. The first is a sample space. A sample space is just the set of all outcomes that could possibly occur. So for example, if we're looking at a die, hopefully a fair die, when we roll it, there's 6 possible discrete outcomes that we could have. You could roll 1, 2, 3, all the way up to a 6. Another example of discrete outcomes that we could get would be a coin flip. If we're flipping a coin, then the 2 possible outcomes that we can have are a heads and a tails. And both of these are examples of discrete outcomes we can have, but it doesn't have to be discrete. For instance, we could look at the weight of all of different corgis that are in the world, and that wouldn't be a discrete weight, that would be a continuous weight, because you can really be any weight, any number of fractional ounces. The important thing to remember is that the sample space defines what are the possible outcomes that can happen. A second important component of a probability space is an event space. An event space is just a set of events that can happen. For instance, one event we might be interested in if we're rolling dice are dice rolls that are even. So that would be 2, 4, and 6. Or we might be interested in dice rolls that are greater than 4, which would be 5 and 6. Your event space is going to be a set of subsets of your sample space, and they have to have the following properties. The first thing that you have to have in an event space is that you have to have the null set, so nothing happened, in that space. Also, if you have a subset in your event space, then you also have to have its complement. So for instance, if we have even dice rolls in our event space, we also then have to have the complement, or the opposite of that, which would be all the non-even, or in this case, odd dice rolls. We also have to make sure that if we have multiple sets in our event space, that the union of those sets is also in the event space. So working from the example we're talking about, if we have the null set, since it has to be there, and we have the even dice rolls and the odd dice rolls, that must mean that the union of even and odd is also in the event space, which means we also have to have all dice rolls, so like any dice roll in our event space. These event spaces are modeled as sigma algebras. And they're not actually unique. So if we have a sample space, omega, then there are actually multiple sigma algebras or event spaces that could be valid. For instance, we could have a sigma algebra that is just the trivial cases. It is just the null set and everything. And if you go back, you can see that if we have an event space with just the null set and everything in its set, then it does follow all of these rules. For instance, the null set is there. The complement of every single thing in our set is also present in our set, right? The complement of the null set would be everything that is also in our event space. And we can see that if there are multiple subsets in our event space, then the union of them is also in the event space. But that's not usually the most useful event space that we could define. So we could also define a completely different sigma algebra that is also valid and follows all of the rules that we just talked about. For instance, we could have the opposite of the trivial case, which is the power set, which includes every single possible subset of our sample space. And if you go back to these rules and kind of work it out in your brain, you can see that if we have every possible subset, then we also fulfill all of these rules here that define what an event space has to be. The last part of our probability space that we need to discuss is a probability function or a probability measure. And this basically takes all of the events that are in our event space and puts them through a function that then assigns them a probability. All of the probabilities have to be between 0, not going to happen, and 1, definitely going to happen. And they have a couple other rules that they have to follow. So the idea here is that our probability function can take in every event that we're interested in that we've defined in our event space, and it can assign it a number, that number being a probability that we can then use in a bunch of different applications. So just like our event space had to fulfill a couple of rules, so do probability functions. The rules that probability functions must satisfy include the following. First, the probability of every single event either has to be 0 or greater than 0 for every event in our event space. And that makes sense. It's not really sensical in most cases to define a negative probability, so we know that our probabilities have to be positive, or at least 0 or positive. The second rule that we have to follow is that the probability of all of the events together has to be 1. Put another way, the probability of something happening, every single possible outcome, the probability of any of those happening has to be 1. Something has to happen. Lastly, we have the rule that if we have a bunch of different events and they're all in our event space and they're disjoint, meaning they don't contain any of the same options of outcomes, then the probability of their union has to be the sum of all of the individual probabilities of those events. In other words, let's say we're rolling dice again and we have a die and we are looking at all even rolls and all odd rolls. Well, those are disjoint sets. Those two events do not have any outcomes that overlap. Even dice rolls are even, odd dice rolls are odd, so they do satisfy the fact that these two sets are disjoint. And just FYI, that's what this little part of the formula is saying. It's saying that the intersection of the sets is the null set, so they don't have any overlap. And we know that the probability of getting an even or an odd dice roll is the sum of getting an even dice roll and the probability of getting an odd dice roll. Now, this might seem like a really simple set of rules, but it actually allows us, with these kind of set theory definitions here that are outlined on the slide, to basically come up with every single rule that we need in order to work with probabilities. Highly recommend you go to the slides, or you can just pause the video here and kind of look at some of these rules. I think they're pretty intuitive, and I've made this figure to sort of help you reason out these relationships here. But in combination with our probability rules, we can do some really powerful things with just a very simple set of rules that our probability function has to fulfill. For instance, here on the slide, you can see a bunch of rules that you've probably seen defined in like a math stats or a probability course. And it's actually the case that you can use all of the set rules and the rules that we have for probability functions to prove these things. So we'll actually maybe do some together in class to sort of see how it is that we can use all of these very basic building blocks of rules to build pretty complicated theorems in probability. All right, I'm going to go ahead and end there. We've basically talked about some foundational ideas in probability, namely what are probability spaces and how do they work. And like I mentioned, one of the things that we'll cover in class and probably throughout the rest of the course is the fact that these rules allow us to do basically everything in statistics. You see on the screen, one of the things we'll talk about in class is conditional probabilities and how we can use probability spaces to kind of think about what do these things like a conditional probability actually mean. All right, that's all I have for you. I will see you next time.